Okay, so let us start with the next thing, that is the half-life of first order reaction. So yesterday we discussed about the integrated rate law for the first order reaction, and we arrived some equations for that. So we'll extend this process to the next level, that is half-life of the first order reaction. Now what does it mean? What does it mean? This is half-life of the reaction. Okay. Now this half-life you can define as, definition of this half-life is, you can define this half-life as, it is the time needed for the reactant concentration, time needed for reactant concentration to fall or to decrease or to reduce, to fall to half of its initial value. So whatever is the initial concentration, whatever the time required to reduce or to fall this value up to the half of its initial value, that is called as the half-life of the reaction. Okay. Now we know that in the earlier lecture, we know that the integrated rate law, this is integrated rate law for first order reaction. So you need to remember these equations. Remember, huh? You need to remember, you will need to learn these equations carefully. Then only you will be able to solve the MCQs based on this, or either the numericals or the both. So this is the integrated rate law for the first order reaction. Log to the base 10, concentration of A at 0 time and concentration of A, that is a reactant, at time t. So where this concentration of A at 0 time, this is the initial concentration. You know this thing, this is initial concentration of A at t equals to 0, isn't it? And that is AT concentration at time t. I'll write this t here. So this is the concentration of A at t equals to t. Okay. Now looking at the definition, that is the amount, that is the time needed for the reactant concentration to fall to half of its initial value. So looking at this definition, the concentration of the reactant, which is the initial one, we are more interested in the initial concentration to decide the half-life. So when it becomes half at time t, so that will be t half. So this t half is nothing but the half-life. Okay, I hope you understood this. So that is equal to t half. Now, when you say this is t half, means here in this case, t is equal to t half, then this concentration of A at time t will be equal to concentration, initial concentration to its half, isn't it? Now, you have this equation in front of you, this one, this equation. Now, if you substitute this value for this in this equation, you have this one, AT is equal to A0, concentration of at 0 time divided by 2. Now, if you substitute this value for this one, look at this, and if you substitute in this equation, you will get the equation right here. So I'll try to accommodate the things on the same slide. So K will be equal to 2.303 divided by T log to the base 10 concentration, this is initial concentration at T equal to 0, divided by concentration of initial concentration to its half. Means what did we do? We just replaced this quantity AT by A0 by 2 because we know that this is T equals to T half, then this AT will be equal to initial concentration divided by T. This thing we did according to the definition of the half-life, isn't it? Now you can simplify further this as 2.303 divided by, now instead of T you can write here T half, okay, and if you do this or if you simplify this, you will get log to the base 10. So A0 will get cancelled. Log 2. So log 2 is nothing but 3.3010. So you can write here this is equal to 2.303 divided by T half into log to the base 10 2, that is log 2 will be 0.3010. Okay, and if you further simplify this, you'll get 0.693 divided by T half. Okay, now I'll try to accommodate the same here on the same slide. So therefore, T half will be equal to 0.693 divided by K. Okay, so we got this equation. So this is again of importance to solve the numericals based on this. So we have this one. After discussing or after applying the concept of half-life to this equation, that is the integrated rate law for first order, we arrived to this equation, that is T half equal to 0.693 divided by K. Okay. Or you can write K equal to 0.693 divided by T half. We are just rearranging the equation, nothing else. So according to this equation, what does it mean? It shows that the half-life of the first order reaction, we are talking about the first order reaction only. So half-life of the first order reaction is constant and it is independent of the concentration of the reactant. There is no concentration term involved here. So you can say that the half-life of the first order reaction is independent of the concentration of the reactant. So this equation is of importance for us, and this is also of much importance to solve the numericals based on this. Now, how do you represent this graphically? So we have this equation in front of us that is about the half-life. We already discussed about this integrated rate law equation in earlier lectures. So now we'll discuss further extent how do we apply this, how do we represent this equation graphically. So let us go to the next slide. Now here you can write the graphical representation of half-life for the, of course, of the first order reaction. Okay, now if you plot the graph for this, we have this equation in front of us, that is T half equals to 0.693 divided by K, isn't it? Now if you plot the graph of concentration of A at time T versus time, you'll get such type of curve. Okay, now this is your time increasing in this direction, and this is the concentration at that particular time. Now how do we apply this to this half-life here, to this equation rather? So if you have such type of curve here, I'll use the another color so that it will be more clear for you. So now you have this graph in front of you. Now if you write here for this one, if I write here T half, means this is the half-life for this particular reaction. Now I can write here twice of this T half. Now I can write thrice of the T half. If you further extend as 4 times of the T half, and so on, 5 times of the T half. Okay, so this is your first T half, that is half-life, means that is the amount reduced to half of its initial amount. So if you go to this graph here, now if you extend like this, you'll get the intersect here. Okay, so this is your first T half. Remember, or you can write here. This will be your first T half value. Now this at this point, whatever is the amount, that will be your initial concentration here. So it reduces to the half. So I can write for the concentration, that is A0 divided by 2. Means for this T half, the concentration will be A0 divided by 2, half of it. Now if you further go for this, twice of the T half. Okay, I hope you are getting me. Twice of this T half. Now if I extrapolate this like this, now whatever is the concentration left here, that would be, you can, for this one, twice of this T half, it would be A0 initial concentration divided by 4. Okay, and this point, this one, this will be your next T half. Now if you further extend this, go to this point, thrice of this T half, and go to this graph. I'll extrapolate this one. Now for this, it would be concentration, initial concentration divided by 8. Means what we are doing, we are just depleting or reducing the concentration of A by 2 times. So this will be A0 initial concentration divided by 8 here for thrice of the T half, and so on. For this one, for 4 times of this T half, it would be, for this point, it would be concentration of A0 divided by 16. Okay, if you go for this one, if you extrapolate this graph, for this point, it would be concentration of initial concentration divided by 32, and so on. Means what exactly we are doing? We are just reducing these values by half. This is T half, this is twice of T half, this is thrice of the T half, 4 times T half, 5 times T half. Means for each and every time, this portion will be your T half. This will be your portion for the T half. This is again your portion for the T half. From this to this only. Okay. So this is your first T half, this is second T half, third T half, this is fourth, and the fifth, and so on. So accordingly, the values for this concentrations will be like this, and so on. So you can represent this half-life in this way. This is not given in your textbook in this manner. I just try to simplify this. Okay, so AT is the concentration of A at time t. Means if you consider this as a half time or half life, that you can plot the graph this way. Okay, I hope you understood this one. Now, what does it means actually? The time required to change the concentration from A0. Wait a minute, I'll just use another one. So means that if you want to change the concentration, so what did we do did just now? That is, we have changed the concentration from A0 to A0 by 2, isn't it? This is the first T half or first half life, which is denoted by T half. Okay. The time required to change the concentration, now your concentration is A0 by 2. And you can change this from A0 by 2 to A0 by 4, isn't it? So this will be your second T half or second half life, and so on. Okay, I hope now it is more clear for you. So it is clear from this graph that the half-life of the first order reaction is constant. It is same here, it is again same here, it is same here. So it means that half-life of first order reaction is constant. This is for first order reaction is constant, because you will be solving MCQs based on this graphical data or graphical representation. So you need to remember this equation, and you need to remember the integrated rate law also. This is about the half-life. Now we'll proceed for the graphical representation of the first order reaction. Now we have this equation that is a differential rate law. We just discussed about the integrated rate law. Now you might be able to draw the graph using differential rate law or integrated rate law. We'll be discussing all the types of equations and how do we apply them to represent the things graphically. Okay, so the graphical representation. This is again of very much importance, remember. So graphical representation of first order reaction. That was of half-life, remember. Now this is of the first order reaction. Now consider a reaction like this. It is getting converted into product and the differential rate law, remember, we are using differential rate law. Rate law for this reaction, you can write here as rate equals to minus of, we have done this exercise already. That is dt, means we are applying a differentiation. So this is equal to K concentration of A at time t plus 0. Okay, now this equation is of the form y equal to mx plus c. So we are applying here the straight line equation. Now here's the graph of rate versus, now I'll draw the graph here. The graph, it was found to be, if the graph is plotted against this concentration of A at time t versus the rate of reaction. So you'll get here such type of graph. Here it is 0. Coordinate here at 0. This is the initial point of this. Now this is the y coordinate. That is the rate. This is nothing but the rate. We plotted it here on the y-axis, isn't it? This is m, that is the slope. Okay, and this is the x coordinate, that is at. So we plotted it on x-axis. So, and plus c, that is the intercept, that is 0. Okay, so this is your 0. Intercept of y at y-axis, that is the, here it is 0, here it is 0. You can see here it is 0. So what does it mean? This you will get here the straight line graph starting from the origin and it is increasing from this point at 0, and as the rate increases, the concentration of this AT also goes on increasing. This law or this graph suggests that as the rate increases, this concentration also goes on increasing, or as this concentration increases, the rate also increases. What is this AT? This is the amount unreacted, isn't it? So as the amount of this concentration of A, it is unreacted, it is increasing. So obviously the rate of the reaction, it will go on increasing. So this is the one way when the differential rate law equation is used, you can interpret the graph, this same equation in this format. So this is for the differential rate law. Remember, you need to remember these graphs also. So differential rate law, such type of graph will be getting. Now, you have this second thing. I'll go to the next slide. This is for the differential one. Now, integrated rate law in different form. So integrated rate law. There are various graphs can be plotted, remember, for this. So for this integrated rate law, you have this equation is equal to concentration of A, initial concentration, E raised to minus KT, isn't it? This is the other way you represent the integrated rate law. Now, if you again apply this y equal to mx plus c, so you'll get such type of graph for this. This time t on the x-axis and this at, that is y here on the y-axis, isn't it? And you will be getting such type of graph. You need to remember such graphs. Okay, so the concentration of the reactant. So how do you interpret this graph here? Looking at this, So concentration of reactant decreases exponentially. Drastic decline is there exponentially with time. So as the time increases in this direction, this concentration, it goes on decreasing. You can see here there is decrease in the concentration here. So it has got some concentration at this point at 0 time. Okay. But as the time goes on increases in this direction, this graph, this curve shows that there is decline in the concentration. So this is the second way. This is the another way of representing the integrated rate law. Now this third one, we'll go to the next one. This integrated rate law equation, it can be written the same one. What I wrote just now, this can be written in this format also. You know this thing. K equals to 2.303 upon T, log to the base 10, concentration at 0 time divided by concentration of A at T time. So on, if you rearrange this equation, you can write KT divided by 2.303 equal to log to the base 10 concentration at 0 time minus log to the base 10 concentration at T time. Okay, we are just rearranging the equation, nothing else. So therefore, you can write in terms of log to the base 10, the amount of reactant which is remain, that is AT, will be equal to K divided by 2.303 into T plus log to the base 10 concentration or the initial concentration. So we are just rearrange the equation, nothing else. Okay, we just brought this on the left hand side and we rearrange this equation here. So we want this in the format of y equal to mx plus c, isn't it? So here it should be minus actually. This should be minus when it comes to this side. This just to uh, remove this minus sign, we can write here minus and here it is plus. Okay, so this will be y equal to minus mx plus c. So what should be drawn on this x-axis? That is time t. Okay, so this will be your x. This is your minus x, means this is your slope. Okay, I hope you understand this. Okay, now this is the straight line equation. Now when you draw the graph for the same equation, what do we are supposed to take on the x-axis? That is your t, that is time. This is your x-axis. This is x. Okay, so you just write here time on the x-axis, and what should be on the y-axis? This is for the y-axis. This is your y. So you can write here log to the base 10 concentration of A at time t. Now, if you plot the graph for this, you will get such type of graph like this. So this is the slope for this graph. This is found to be this one. So this is m, means this is slope. I hope you know this thing. So this is your slope. The slope will be equal to minus k divided by 2.303. Means once you found the slope, you will be able to find the value for k. Means rate constant can also be calculated by looking at the graph. Okay, so this is the way, this is the graph of AT versus time t, and this is your slope here. So therefore, k, that is rate constant, can be calculated like this, minus 2.303 into slope, isn't it? Slope can be found out this way, isn't it? So this coordinate and this coordinate, I hope you know this thing. This is a very simple thing. So slope can be calculated and you will get the value for this rate constant. So this is the graphical representation for the integrated rate law equation. This type of graph you will be getting. The same thing we did for the integrated rate law here also. But we wrote this equation in different form and we got this thing. Okay, the same equation, integrated rate law equation, if you write in this format, you are getting this type of graph. Okay, now this is the third way you can represent the first order reaction. Now There is one more way you can represent a first order reaction. Now the integrated rate law, we have this thing, K is equal to 2.303. This is again integrated equation, integrated rate law for the first order. Of course, for the first order. This is for the first order integrated rate law. Wait a minute. Integrated rate law of first order reaction. There should be no confusion. We are just right now we are discussing about only about the first order. Log to the base 10, concentration, initial concentration and concentration at time t. Now on rearrangement of this equation, you can rearrange the equations and you can plot different graphs also. In addition to this, you can plot the graphs also. Not necessary that this much is only can be done. Whatever I'm just telling you. Plus 0. Okay. So this is the way, another way you can write the equation by rearranging this. So this is again a y equal to mx plus c. Okay. Now y, this is your y, this is your slope, and this is your x-axis. So if you plot the graph for this, what should be taken on x-axis? That is time. And on y-axis, that is log a0 by 80. Okay. Now, if you plot the graph for this, you'll get such type of graph like this. And the slope for this is this. This is your slope. M means the slope of the graph. So for this particular graph, slope will be equal to k divided by 2.30. Okay. Now, the graph for this log of a0 by 80 versus time, here, it is a straight line passing through the origin here, and this is your slope. So the same equation, the same one that is the integrated rate law, this can be represented graphically this way also. So this is the another way. You are getting such type of graph here. So you need to remember the equations in the rearranged form and apply straight line equation to those. So we are getting such type of graph. So you need to remember what is to be taken on the x-axis and what should be there on the y-axis. So here, what is this 0? This is the y coordinate here. It is 0, isn't it? This is the 0. Okay. Now this is the one way of the graph interpreting the first order equation, integrated rate law for the first order. This is the another way. If you write this way, and the graph is plotted against log 80 versus time t, you will get such type of graph. This is the third way. You can put the integrated rate law, you will be getting such type of graph. Okay. And this is the differential rate law. This is for the differential rate law. So these are the three or the four different ways you can interpret the first order reaction graphically. Okay. Now, what are the different examples for the, remember, you need to remember all these equations and apply the straight line equation to those. And so you will be easily able to plot the graph, or the MCQs are asked in this way that you are given the different graphs. So for that purpose, you should be very sure what is to be on the y-axis and what should be there on the x-axis. Then only it is possible for you to identify or to answer the MCQ. Now there are different reactions for the first order, that like the decomposition of H2O2. There are different examples, but which are commonly asked in examination, or many times they are repeated. That is the decomposition of H2O2. This is the first order reaction. Then decomposition of N2O5. This is again first order reaction. Conversion of cyclopropane to propene. This is also a first order reaction. So the rate for this reaction can be written as K into concentration of H2O2. For this one, you can write rate equals to K into concentration of N2O5. And for this one also, you can write rate equals to rate of the reaction equals to rate constant into concentration of C3H6, that is cyclopropane. So these are the few examples which you will be coming across in your numericals or in the MCQs also many a times, decomposition of H2O2, N2O5 and so on. So for this, obviously you will be able to write the reaction. You did not have to worry about the reaction. So you can write the reaction for this, or the reaction rather those are given, balanced reactions are given. And you need to calculate the rate, order and so on. So from the given data, you will be able to find out the or solve the either numericals or MCQs and so on. So this thing we'll be discussing in due course of time. Don't worry about this. I'll be providing you the different videos, or I'll conduct the live lectures also, solve the numericals and the MCQs based on this. How do we approach for this type of problem? So this is about the um, first order reaction, and then next we will talk about this zero order reaction in next lectures.